and they found lost water in Mars. Recent scientific investigations have unveiled what has been termed the lost water of Mars, revealing a staggering volume that could potentially fill multiple oceans. This discovery marks a significant milestone in our understanding of Martian hydrology and suggests that the planet may harbor more water than previously anticipated. However, despite this abundance, the practical implications for future colonization efforts remain limited. The largest reservoir of water identified to date on Mars exists within a complex network of tiny cracks and pores embedded in the Martian crust. These geological formations are situated at considerable depths, specifically between 11.5 and 20 kilometers below the surface. The presence of water at such profound levels raises intriguing questions about its origin and the geological processes that have allowed it to remain stable over eons. While this underground reservoir represents a remarkable find, its accessibility poses significant challenges for potential human explorers. The water is not readily available in liquid form on the surface. Instead, it is trapped within the rock matrix in a diluted state. This means that extracting usable water for drinking, agriculture, or other essential needs would require advanced technologies capable of reaching these depths and effectively processing the water contained within. Moreover, understanding how this subsurface water interacts with Martian geology is crucial for future missions aimed at establishing a human presence on Mars. Researchers are keenly interested in exploring whether this hidden reservoir could support microbial life forms or contribute to our knowledge of past climatic conditions on the planet. As we continue to explore Mars through various missions and technological advancements, this discovery emphasizes the importance of ongoing research into Martian resources. It highlights both the potential and limitations associated with utilizing these subsurface water reserves for human habitation. Future exploration strategies must consider innovative methods for accessing and utilizing these resources while also addressing the broader implications for planetary science and astrobiology. In conclusion, while the discovery of substantial amounts of lost water beneath Mars' surface offers exciting possibilities for understanding our neighboring planet's history and geology, it simultaneously underscores the complexities involved in harnessing these resources. In a groundbreaking discovery made just a few months ago, scientists have revealed the unexpected presence of water and morning frost at the Martian equator. This finding challenges long-held assumptions about the planet's climate and hydrology, as it was previously believed that such conditions could only exist in the colder polar regions, where water is more readily available. The implications of this discovery are profound and far-reaching. By identifying viable sources of water in the equatorial region, researchers have significantly expanded the potential sites for future human colonization on Mars. Previously, plans for establishing colonies were largely confined to the polar areas, where ice deposits are abundant, but present their own set of challenges related to extreme cold and seasonal variations. The newfound availability of water at lower latitudes opens up exciting possibilities for sustainable human habitation. Water is a critical resource for any long-term settlement, not only for drinking, but also for agriculture, oxygen production, and even fuel generation through processes like electrolysis. The presence of morning frost suggests that there may be accessible moisture that could be harvested or utilized in various ways to support human life. Moreover, this discovery prompts further investigation into the climatic conditions at the equator and how they might support life, both microbial and potentially human, in ways that were previously unconsidered. Understanding how water exists in these warmer regions could provide valuable insights into Mars's geological history and its capacity to sustain life. As we look toward future missions aimed at exploring Mars more thoroughly, this revelation underscores the importance of adaptive exploration strategies that consider a wider range of environments. It encourages scientists and engineers to rethink their approaches to habitat design, resource utilization, and overall mission planning. In conclusion, the discovery of water and frost at the Martian equator not only reshapes our understanding of Mars's environmental dynamics, but also significantly enhances our prospects for establishing human colonies beyond the polar regions. This exciting development paves the way for new research opportunities and technological innovations that could ultimately facilitate humanity's journey to becoming an interplanetary species. The question of Mars's water has long puzzled scientists and researchers. Given that the planet once boasted vast oceans, flowing rivers and expansive lakes, until approximately 3 billion years ago, it stands to reason that there should be significantly more water present than what is currently found in the polar ice caps. The apparent scarcity of accessible liquid water on the surface raises critical questions about its fate over geological time. Recent studies have begun to shed light on this enduring mystery. Evidence suggests that much of Mars's original water may not have simply evaporated into space or frozen into permanent ice. Instead, it could be trapped within the planet's crust. This includes being absorbed into minerals or existing in a diluted state within tiny fractures and pores in the rock formations beneath the surface. The discovery of substantial amounts of lost water in these underground reservoirs indicates that Mars still harbors significant quantities of H2O, albeit in forms that are not easily accessible for human use or exploration. This finding aligns with recent observations of water and frost at lower latitudes, further supporting the idea that Mars has a complex hydrological history that extends beyond its current polar ice reserve. Understanding where this lost water resides is crucial for future exploration missions aimed at establishing human colonies on Mars. If scientists can develop methods to extract and utilize this subsurface water effectively, it could provide a vital resource for sustaining life on the planet. Moreover, studying these hidden reservoirs may offer insights into past climatic conditions and help us understand how Mars transitioned from a wetter environment to its current arid state. In conclusion, while much remains to be learned about the distribution and availability of Martian water, recent discoveries are beginning to unravel the mystery of its loss over billions of years. As we continue to explore Mars with advanced technologies and missions, we may uncover even more secrets about its hydrology and potential for supporting future human habitation. This ongoing research not only enhances our understanding of Mars, but also informs broader questions about planetary evolution and the potential for life beyond Earth. Recent advancements in our understanding of Martian hydrology have been propelled by groundbreaking research utilizing seismic data gathered from NASA's InSight mission. An international team of geophysicists has made a remarkable discovery: a vast underground reservoir of water beneath the Martian surface. This reservoir is so extensive that it could theoretically inundate the entire surface of Mars, with an ocean ranging from 1 to 2 kilometers in depth. The implications of this discovery are profound for both planetary science and future exploration efforts. The existence of such a significant volume of water hidden beneath the surface suggests that Mars may have retained more of its ancient hydrological features than previously thought. This challenges earlier assumptions about the planet's capacity to support life and raises intriguing questions about its geological history. The findings were recently published in the Proceedings of the National Academy of Sciences, highlighting the importance of interdisciplinary collaboration in advancing our knowledge of extraterrestrial environments. By employing sophisticated seismic techniques, researchers were able to penetrate deep into Mars's crust, revealing insights into its composition and structure that were previously inaccessible. Understanding the location and characteristics of this underground water reservoir is crucial for future missions aimed at human colonization. Water is essential for sustaining life, and having access to such a substantial resource could significantly enhance the feasibility of long-term human presence on Mars. It opens up new possibilities for agriculture, drinking water, and even fuel production through chemical processes. Moreover, this discovery invites further investigation into how this water became trapped within the Martian crust and what geological processes have allowed it to remain stable over billions of years. It also raises questions about potential microbial life forms that may exist within these subterranean environments. In summary, the identification of a massive underground water reservoir on Mars represents a significant milestone in our exploration of the Red Planet. As we continue to analyze data from missions like InSight and plan future explorations, this finding not only enriches our understanding of Mars's past, but also enhances our prospects for establishing human colonies in the future. While the discovery of a vast underground reservoir of water on Mars is undoubtedly a significant achievement for scientists and researchers, it presents considerable challenges for future colonization efforts. The primary issue lies in the nature and location of this water. It exists in a highly diluted state within tiny fractures and pores in the Martian crust. More critically, this reservoir is situated at depths ranging from 11.5 to 20 kilometers beneath the surface. Accessing such deep-seated water reserves poses formidable technical and logistical challenges. On Earth, drilling to similar depths often requires advanced technology and substantial resources, making it a complex endeavor even in our own geological context. The harsh conditions on Mars, characterized by extreme temperatures, radiation exposure, and dust storms, would further complicate any attempts to reach these depths. For future Martian colonists, this means that while the presence of water is encouraging from a scientific perspective, it may not provide an immediate solution for sustaining human life on the planet. Water is essential for drinking, agriculture, and various industrial processes. However, if it remains trapped deep within the crust, alternative strategies must be developed to secure accessible sources. Researchers are now faced with the challenge of identifying more readily available water sources on Mars's surface or near-surface environments. This could involve exploring polar ice caps or investigating potential subsurface aquifers that might exist at shallower depths. Additionally, advancements in technology may one day enable us to extract water from deeper reservoirs more efficiently. In conclusion, while the discovery of a massive underground water reservoir on Mars represents a remarkable scientific milestone, its practical implications for human colonization are limited by accessibility issues. As we continue to explore Mars and develop new technologies for resource extraction and utilization, addressing these challenges will be crucial for establishing sustainable human habitats on the Red Planet. In addition to its implications for future colonization efforts, this remarkable discovery of a vast underground water reservoir on Mars opens up new avenues for astrobiological research. If scientists can eventually devise methods to access this reservoir, it could become a focal point in the search for potential life forms that may have existed or may still exist beneath the Martian surface. The presence of water is a critical factor in determining habitability. Thus, understanding where this water resides and its characteristics could provide valuable insights into Mars's capacity to support life. As Vashan Wright from the University of California, San Diego, one of the authors of the study, notes, comprehending the Martian water cycle is essential for unraveling the complexities of Mars's climate evolution, surface processes, and internal dynamics. This discovery serves as a crucial starting point for researchers aiming to piece together Mars' geological history. By identifying not only where water is located, but also quantifying its volume and distribution within the crust, scientists can develop more comprehensive models of how Mars has changed over billions of years. Such models are vital for understanding past climatic conditions and assessing how they might inform our knowledge about planetary evolution more broadly. Moreover, this research underscores the importance of continued exploration and technological innovation in planetary science. As we advance our capabilities in remote sensing and subsurface probing techniques, we may uncover even more hidden reservoirs or signs of ancient aquatic environments that could further illuminate Mars's past. In summary, while immediate practical applications for human colonization may be limited due to accessibility challenges, this discovery significantly enriches our understanding of Martian geology and hydrology. It lays important groundwork for future investigations into both the planet's history and its potential for hosting life, past or present, making it an exciting area of study as we continue our exploration. In a significant advancement in our understanding of Martian geology, Vashan Wright and his colleagues, Michael Manger from the University of California, Berkeley, and Matthias Morzfeld from the Scripps Institution of Oceanography, utilized data gathered by NASA's InSight mission to develop a comprehensive model explaining the presence of water beneath Mars's surface. By applying a mathematical model rooted in rock physics, which is commonly used on Earth to identify underground aquifers, they were able to interpret the seismic data collected during InSight's operational period from 2018 to 2022. The researchers concluded that the most plausible explanation for the seismic readings was a deep layer of fractured igneous rock, essentially cooled magma, that is saturated with liquid water. This finding not only sheds light on Mars's geological history, but also suggests that significant amounts of water may be trapped within its crustal structure. Throughout its mission, InSight recorded numerous seismic events on Mars, including earthquakes with magnitudes reaching approximately 5 and impacts from meteorites. The detection of these seismic waves provided invaluable insights into the planet's internal structure. By analyzing how these waves traveled through different geological formations, geophysicists were able to infer details about Mars' composition and behavior. The ability to detect and analyze seismic activity has opened new avenues for understanding not just where water might be located, but also how it interacts with Martian geology. The presence of liquid water within fractured igneous rock could have implications for both past habitability and future exploration. Vashon Manga expresses his enthusiasm regarding the findings from NASA's InSight mission, stating that it has significantly surpassed his initial expectations. The comprehensive analysis of seismic data collected by InSight has provided critical insights into various aspects of Mars' geological structure. Researchers were able to determine key features such as the thickness of the Martian crust, the depth and composition of its core, and even temperature variations within the mantle. One particularly exciting outcome from this research is the confirmation of a substantial reserve of liquid water beneath Mars's surface. This discovery not only enhances our understanding of Martian geology, but also offers valuable clues about past climatic conditions on the planet. As Manga notes, water is essential for life as we know it. Thus, it raises intriguing possibilities about whether this underground reservoir could still serve as a habitable environment today. Drawing parallels with Earth, Manga points out that extreme environments such as deep mines and oceanic trenches are known to host diverse forms of life. While no direct evidence of life has yet been found on Mars, identifying locations with potential habitability is a significant step forward in astrobiological research. To date, planetary scientists have launched over 40 missions, comprising both probes and landers, to Mars with the goal of unraveling the mysteries surrounding its water history. These missions aim to answer critical questions about what happened to the planet's once abundant water resources. When was it lost? Where did it go? And could it have ever supported life? Traditionally, it was believed that much of Mars' water escaped into space due to atmospheric loss. However, recent discoveries challenge this notion. New research suggests that a significant portion of this water did not vanish into the cosmos, but rather infiltrated deep into the Martian crust. This revelation opens up exciting possibilities for understanding Mars's geological and hydrological history. The researchers propose that if the crust is relatively uniform across different regions of Mars, then there may be substantial amounts of water trapped within this mid-crustal zone, potentially exceeding the volumes thought to have filled ancient hypothetical oceans on the planet. This finding implies that rather than being entirely lost, much of Mars' water may still exist beneath its surface. The implications are profound. If large reserves of liquid water are indeed present underground, they could provide crucial insights into Mars's past climate and its potential for habitability. The next challenge for scientists will be developing methods to access these hidden reservoirs. As exploration technology advances, future missions may focus on drilling or probing deeper into the Martian crust. In summary, while we have made significant strides in understanding Mars's water history, much work remains ahead. Subscribe and like for more information like this.